Hi guys again.
Hello.
Hello.
Okay, I think we can start slowly but surely. Okay, so I want to cover several topics for today. I want to discuss the extended Euclidean algorithm with and apply it to polynomials with coefficients in different fields. And then I want to discuss irreducible polynomials when the field has finitely many coefficients like z2, z3, etc., how to find them. And then I want to discuss properties of the ring of reminders and the Chinese reminder theorem, how to apply it in different situations. Okay, so let's move on. First of all, yeah, just in case, do you ever try to apply the extended Euclidean algorithm for polynomials? Do you know about this algorithm?
Yes.
Okay, so you know how to compute all these things.
More
Okay.
or less.
Okay, so I think if we repeat, it doesn't hurt. So suppose we have a polynomial ring like this, and the polynomial f is something like this: x to the fourth plus 2x cubed minus x squared minus 4x minus 2. And g is something like x4 plus x cubed minus x squared minus 2x minus 2. Let's try to compute the GCD of these two polynomials. So how do you do this? Well, you need to divide one polynomial by the other one with remainder. Well, let me show you how to organize the computation. So let's divide f by g. So we need to represent it in the form something times g plus something of degree smaller than g. Well, as you can see, we can multiply g by 1 and subtract from f. And what will we get? We will get x cubed minus 2x, if I'm not mistaken. Yeah, we subtract this cancels, this one also, and yeah, x cubed minus 2x. This is your q1, and this is your r1. Now we move g into the place where f was, and we move r1 into the place where g was. And now we want to divide g by r1 with remainder. Well, so we need to divide this guy by this polynomial. Well, I'm prepared for this seminar, so I know the answer, what will be here, but you need to divide, well, you need to do this computation by hands, but the answer will be this. Here it must be x plus 1, and the remainder will be x squared minus 2. So if you compute this, you will get these results. And this will be your q2, and this is r2. But just in case, is there anyone who needs an explanation how I found these two polynomials?
Yes,
Okay.
can you explain this?
Okay, so let me do the computation here on the right. So this is the way I'm doing this. So x4 plus x cubed minus x2 minus 2x minus 2. This is g. And now I want to divide it by r1. So I'm writing it like this, x cubed minus 2x. Now, so first of all, this is the highest term here, and this is the highest term here. I want to cancel the highest term in g. So I need to multiply this expression by x. So, and subtract from g. So after multiplying x cubed minus 2x by x, you'll get x fourth minus 2x squared. And I subtract one polynomial from the other one. So these guys are canceled. And then what I have, x cubed then minus x squared plus 2x squared will be x squared minus 2x minus 2. Now I want to cancel x cubed. So I need to multiply x cubed minus 2x by 1 and subtract. So I will get x cubed minus 2x, and I subtract this result. So these guys are canceled, and also these guys are canceled, and the result will be x squared minus 2. And then this is your Q2, and this is your R2. So this is the way how to compute the remainder and the quotient. Is it clear?
Sure.
Okay. Is there anyone who needs some other explanation or clarification? Okay. So now I need to proceed. So here I put R1 instead of G, and I move R2 in place of R1, and I want to divide R1 by R2 with remainder. Well, and here, as you can see, R1 is this expression, R2 is this expression, and this one is equal to this one times x. So here we have x, and here we have 0. So this is your Q3, and this is your R3. And now we need to stop. So now there are two questions. What is the GCD? And the second question is how to represent the GCD as the linear combination of f and g. The answer to the first question is this. The GCD is the last non-zero remainder. This is GCD of f and g. So you do this procedure. The first time you get 0, you go one step back, and this is your GCD. Now, just in case, is it clear why this is the answer, or should I explain? Is there anyone who needs to explain? Igor?
Yes. Why is it the GCD?
Okay. So you see, well, we want to find the GCD of f and g. Now, I can. The claim was that the GCD of f and g is the same as GCD of g and f minus q1g. Okay, and f minus q1g is just R1. So the GCD of this pair is exactly the same as GCD of this pair. That follows from the claim from the lecture. Okay?
Okay.
Then GCD of this pair is exactly the same as the GCD of this pair. But in this case, you see R1 is divisible by R2. So the GCD of these two guys is this one. And this is exactly the last non-zero remainder. So if I proceed here, then I replace R1 and R2. And then, well, this becomes R2, 0. If I do one more step, because here is R3. So, and the answer here is R2. So this is how the algorithm works. Igor, just in case, is it clear now why this is GCD?
Yeah, it's clear.
Okay, so this is how to find the GCD. Well, just in case, it may happen that, well, you see the GCD is not uniquely defined. Well, if you fix its leading coefficient and say that, let's suppose you want it to be monic, so the leading coefficient is 1, then the GCD is uniquely defined. But when the coefficients of the polynomials are not that pretty as here, it may happen that you have like very, very, how to say, rubbish coefficients here. well, you may divide by these coefficients if you are interested in GCD up to some coefficient. But okay, so now we know the GCD. How to find the expression for the GCD? So let's say this is D, and we know that the polynomial D must be presented as U times F plus V times G. So how to find these polynomials U and V? Well, actually, you can use this information to recover U and V. How do you do that? Well, you see here, R2 can be presented as a linear combination of G and R1. But then you see R1 came from here, and it can be represented as a linear combination of F and G. So let's write this down. So R2 is G minus X plus 1, R1. This is what's written here. If I go up, then R1 is this polynomial, and it's a difference between F and G. So this guy equals F minus G from this equation. So R1 is equal F minus G. And you can substitute this expression here. And then we will get, yeah, and R2 is actually the GCD. So the GCD equals G minus X plus 1. And here, instead of R1, we have F minus G. And now I just want to open the braces, and I will get minus X plus 1, F, and then plus G plus, oh, here it will be X plus 2G. And this is your U, the wrong color. This is your polynomial U, and this is your polynomial V. Well, as you can see, the coefficient, the leading coefficient here could be anything. It's not these polynomials U and V need not be monic. So this is the way how to find these two coefficients. And in general, you use this method. So you just organize all computation in a similar way. Just divide F by G and write down this expression. Then move G here, the remainder here, and you divide this guy by this one, move the remainder here, move these guys here, and so on and so on.
Well, but in our case, we have only 2 reminders. What if I have, say, 100 or 1,000 reminders?
Well, it means that you're very unlucky, and it's unfortunate, but you have to go, you have to make like 100 steps up. So if you have R like 100, you can express R100 as a linear combination of R99 and R98. Then you can represent R99, R98 as a linear combination of the previous ones, just making this substitution. So you just substitute expression from here to the next line, and you go down, 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 and then you have this representation for the last non-zero remainder. Yeah, it's a hard work.
Cool.
But at least I hope that the way how you get the answer should be clear. Are there any questions regarding this computation? Should I clarify the details or repeat something, or maybe you have some comment? Okay, so let's try doing this with a different field. So now we did all the computation for the field of real numbers. It's not very unusual for us, but let's try a different field. Let's take Z2 of X. We know that Z2 is a field. It contains 2 elements, but this is a field, a finite field, a field with 2 elements. Let's take F to be X cubed plus X and G to be X cubed plus 1. Okay, and let's try to find a GCD of these 2 polynomials in Z2. Okay, so how would you do this? First of all, you want to divide F by G with a remainder. So how do you do this? Let's compute Well, first of all, you need to multiply by 1 and subtract. Well, in case of Z2, subtraction and addition is the same thing, because here 1 and minus 1 is exactly the same thing, so you can just add all things together. So as you can see, this is your Q1 and this is your R1. So here we have 1 and different color, 1, and here we have x plus 1. Okay, now we want to divide G by x plus 1. Okay, so we need to move G here, and we'll move R1. So this is Q1, this is R1. And let me write R1.
But don't we have a mistake? So R1 must be x minus 1.
But there is no difference between minus 1 and plus 1 because we're in Z2. So Z2 consists of two elements, 0 and 1. And yeah, and minus 1 equals 1 in this field. Because 1 plus 1 equals 0, so 1 is also a minus 1. So there is no difference between addition and subtraction. And this is a very cool thing with finite fields. The arithmetic is very simple. And you can compute faster. And there are even methods doing the following. If you want to compute something with rational coefficients, you can go to remainders modular very large prime number, do some computation, which is very fast, and there is a way how to recover the rational solution, well, if the prime number was sufficiently large. So for different problems, there are methods of recovering the rational solution from the solution modular some large prime number. So this is one way of making the computation fast. Okay, let's proceed. So now I want to divide G, which is what, x cubed plus 1 by x plus 1. So how would I do this? Okay, so
x squared, mean
yep.
x squared.
Yeah. Now we have x squared plus 1.
Yeah, x
Yeah, again,
plus x is the same as minus x.
Yeah, it's the same as minus x, and then we'll have x plus 1. And now we have 1, which is x plus 1, and this is 0. So as you can see here, x squared plus x plus 1, and here we have 0. So the GCD here is this. So x plus 1 is actually GCD of x cubed plus x and x cubed plus 1. And how do you get the expression? Well, here the expression is really simple. You can get the required expression from one line. So this is just f minus g. So 1, this is your u, and minus 1, this is your v. So this is 1, and this is minus 1. So this is how you deal with finite fields. Now let's try another example. But before doing that, are there any questions?
No.
Yeah, and as you can see, it's very convenient to compute in Z2. Let's try Z3. And I want to show you one important thing regarding computation in Z3 and similar stuff. So now I want to take f to be x cubed plus x plus 1. And I want to take g to be 2x squared plus 1. As you can see here, what's new, the leading coefficient is not 1. Well, in this situation, before doing any computation, just divide everything by this leading coefficient. So instead of considering the polynomial g, consider, well, I'm writing 1/2, which means the inverse element in Z3 corresponding to the element 2. Well, since element 2 is the same as -1, the inverse will be also 2. But I just want to clarify the notation. This is not a rational number. Saying 1/2, I mean the inverse element in Z3. So I want to switch to a new polynomial. Then it makes G prime monic, then compute GCD for F and G prime, and then multiply the result by 2 again to go back to the pair of F and G. So let's do this. So first of all, in the field Z3, 2 is equal to -1. So its inverse is just 2. So if you multiply by 2, you will get G prime is equal to x squared plus 2. Or you can use this notation, x squared minus 1, because 2 and -1 are just different names for the same element. And now we can find the greatest common divisor. So we divide this guy by x squared minus 1. Well, it's easier to deal with +1 and -1 instead of 1 and 2. So that's why I'm using -1 instead of 2. And again, let's try to compute. So we multiply by x, and we will get x cubed minus x. And let's subtract one from another one, and then we will get 2x plus 1. And now, well, yeah, and this is the remainder. So f equals x times g prime plus 2x plus 1. And okay, so now I just want to multiply g prime back by 2. Well, I just want to multiply g prime by 2 in order to get the the initial polynomial g. So if I do that, I multiply g prime by 2 and get g, but I also need to divide x by 2, which means I need to take minus x. Okay, now I have the first expression. Now I want to move g here and this polynomial here, and I get g should be divided by this one, and I want to compute the remainder. And again, here it's easier to divide g by the polynomial x plus 2 or x minus 1. So 2x plus 1 is minus, okay, let's do it in several steps. So I can move 2 outside. So this will be x plus 2. So let me divide g by x plus 2 with the remainder, and then I multiply the factors by 2 again. So what is g? It's x squared minus 1, and I want to divide it by x minus 1, but because x plus 2 is x minus 1. Well, but here it's clear actually that x squared minus 1 is divisible by x minus 1. You just multiply it by x plus 1, and you will get this, and the result will be 0. So in this case, what we have, that g equals x plus 1 times x minus 1. And if I multiply this by 2 and this by minus 1, this will be 2x plus 1. So so this will be the element here, and 0 will be the remainder. So minus x minus 1 is here, and 0 is here. So this is how you can compute. So at each step, I cancel the leading coefficient, and then I move it back. And now again, the greatest common divisor is this expression. And using exactly the same method, well, and actually here you see that the expansion for the greatest common divisor is this, is f plus xg. So 1 will be u and x will be v. So in this case, it's also simple to recover u and v. So are there any questions regarding this computation?
Yeah, I didn't understand.
Okay, so let me do this again. So what I'm doing, I'm just repeating exactly the same algorithm. But there is a problem. The
I
leading
mean, first of all, like, what are we trying to find initially?
okay, we're trying to find the greatest common divisor of f and g. And here is the computational problem. The leading coefficient is not 1, so it's inconvenient. So what I'm saying, if you want to divide f by g, it's more convenient divide f by g prime, which is g over 2. So you just want to cancel the leading coefficient, then divide f by the polynomial g without leading coefficient, and then go back to the initial polynomial g. So how do you cancel? You can multiply g by 2 inverse, which is 2, and normalized g is x squared plus 2 or x squared minus 1. So you divide f by this guy, and you will get. So let me write it here. So I mean, let's try to divide f by g. So just use this this straightforward computation. So x, oh, the wrong color. So if you just repeat the algorithm, you can repeat the algorithm, but let me show you why it's inconvenient. So when you need to divide this one by this one, well, it's inconvenient to find the appropriate coefficients because here you have 2, and you need to find, well, it's easy to get the required monomial part, which is x, because x times x squared gives you x cubed. But now you need to find the right coefficient. And here you need to compute this coefficient, which is 2 in our case. And now when you multiply these guys, you will get x cubed, and then plus 2x. And you want to subtract one from the another one. And after subtraction, well, you will get minus x plus 1. Or am I crazy? Yeah, that's exactly it. Yeah, but assume that this polynomial is larger. So you have multiple steps. Well, in multiple steps, you need to find this coefficient in the following way. You need to divide by this one and multiply by the corresponding coefficient of the term you want to cancel. So it's very inconvenient to have this element 2 here. So I want to simplify this computation. So instead of dividing by 2x squared plus 1, I want to divide this polynomial by 2. So just let's divide this by 2. Well, I will multiply by 2 inverse, and this guy becomes x squared plus 2, or x squared minus 1, which is the same in Z3. And now instead of dividing by 2x squared plus 1, I will divide this by x squared minus 1. And here it's easier because since leading coefficient is 1, I don't have this issue. I just multiply by x. And get this. So, but what did we do? Well, we represented x cubed plus x plus 1, which is f, as x times, well, not exactly the polynomial we wanted. Yeah, but the remainder, as you can see, is exactly the same because 2 is minus 1. But these parts are different. But why they are different? Well, if I multiply this by 2 again and this by 2 inverse, this becomes the initial polynomial g, and this is the quotient from here. So that this was a way to handle the computation in case when the leading coefficient is not 1. So this is one of the ways how to simplify the computation. Well, was it clear now? I'm not sure that it was clear, but I was trying to explain.
It was clear only. Why is 2 inverse equal to 2? And this, it's like,
oh, because 2 times 2 is 4, modulo 3 is 1. Because we are living inside the 3. It has 3 elements, 0, 1, and 2. And how do you multiply elements here? You multiply and take remainder modulo 3. So 2 times 2 is 4, and modulo 3 is 1.
Oh, okay, yeah. Okay.
Or 2 is equal to -1, and for the element -1, it's clear that -1 times -1 is 1. So that's why 2 inverse is actually 2.
Yeah, okay, yeah, that was easy. Sorry.
No problem, no problem. So, but the disadvantage that you need to divide by the leading coefficient each time when you have, this large leading coefficient. For example, you see the remainder here also has an unidentity element as a leading coefficient. So you have to repeat this procedure on each step when you have a strange leading coefficient. But if you are not sure how to do this improvement, or rather, if you, well, it's not, maybe it's not improvement for you. If you want to compute without doing all this stuff, you may do it in a straightforward way, as I did here. Just use the way, just use the method you understand. So if you are not sure what I was talking here about and how to use this efficiently, just use the usual algorithm, but be aware of computing the correct coefficient each time when you do this division, when the leading coefficient is not 1. Okay, are there any other questions regarding this computation? Okay, so let's move on and let's switch to a different problem. Now I want to discuss irreducible polynomials. Okay, let me see. Yeah, so irreducible polynomials. Oh. Okay, so suppose, well, F is a field, and we have a polynomial here. Well, what does it mean that this polynomial has a root? Well, if alpha is an element of F, and F of alpha is equal to 0, then we know that F is divisible by x minus alpha, which means that F can be presented as x minus alpha times g of x. Well, F of x can be presented like this. So if we have a root, then we're divisible by a linear polynomial x minus this root. So if a polynomial is irreducible and nonlinear, it cannot have roots. So from that, it follows that if F is irreducible and the degree of F is not 1, then it has no roots. And just in case, do I need to repeat what does it mean that F is an irreducible polynomial? Should I repeat this, the definition?
Just briefly.
Okay, so irreducible means that you cannot, well, first of all, it's not invertible, so it's not constant. And second, it cannot be presented as a product of non-constant polynomials. Well, let's start with an example. Well, for example, polynomial x is always irreducible. So you can represent it as, let's say, 2x times 1 over 2. Well, let's say in R of x, if we deal with R of x. So yeah, this is the factorization of your polynomial. This is the first factor, this is the second factor, but the second factor is constant. But there is no way to factorize this polynomial in the product of two non-constant polynomials. Why? Because of the degree. If you can, well, if x is the product of f times g, and f and g has non-zero degree, this is equivalent to saying that they are non-constant, then the degree of f is strictly, the degree of f is not smaller than 1. The degree of g is not smaller than 1. And the degree of their product must be not smaller than 2. So x, it's impossible to represent x in such a form where f and g are non-constant. One of them is not constant. So a linear polynomial is always irreducible, but you can find these stupid factorizations because, well, for every non-zero number, you can multiply by this number and divide by this number. So this is the reason why we're interested in monic irreducible polynomials. Okay. Okay, so yeah, so this is a necessary condition. So if you have an irreducible polynomial, so linear polynomials are fine, they are all irreducible. But so we are interested in nonlinear irreducible polynomials, how to find them? Well, first of all, if your polynomial is irreducible, it may not have roots. But if your polynomial has degree 2 or 3, this is a criterion. So suppose f is a polynomial and the degree of f is 2 or 3. Then f is irreducible if and only if it has no root. Has no roots. Let's try to check this. Okay. Well, we already know that this implication always holds. This is okay. So why, if your polynomial of degree 2 and 3 has no roots, then it's automatically irreducible? Well, suppose not. Suppose your polynomial f can be presented as g times h. Now, let's check the degrees. So the degree of g plus the degree of h must be 3. And we know that the degree of each polynomial is at least 1 because we assume that g and h are non-constant. But then what are the options for the degree of g and h? We have two options. Either the degree of h is 1 or the degree of g is 1 and the degree of h is 2. Or the second option, the degree of g is 2 and the degree of h is 1. So in either case, one of these two polynomials, yeah, that's for the degree 3. But here I consider the case of degree of f is 3. Yeah, but in either case, either g or h is a linear. But if g or h is linear, this simply means that f has a root. Because if f is divisible by a linear polynomial, it has root. So from this, it follows that f is divisible by a linear polynomial. Hence, it has root. And this is a contradiction in case the degree of f is 3. In case the degree of f is 2, is similar. In this case, 2 is equal to the degree of g plus the degree of h. In each case, the degree of g and h must be at least 1 because, well, if f is reducible, g and h must be non-constant. But in this case, we have only one option. The degree of g and the degree of h must be 1. So both factors are linear. So again, we have the same thing. F is divisible by a linear polynomial, so it has root. So now we have a contradiction in case of the degree 2. So the second case is also covered. So this proves the claim from the right to left. Just in case, is it clear? Who thinks that it's clear? Plus in the chat. Or minus if you think that it was awful. Oh, okay. Yeah. Okay, is there anyone who needs an explanation or some extra details regarding this? Okay. So now let's do the following. Okay, so suppose we're given well, no, oh, okay. So now the next, yeah. And by the way, in case of polynomials of degree 4, is it true or not? Well, is this claim true when we take the polynomials of degree 4? So is it true that f is irreducible if and only f has no roots? How do you think?
Yes.
Okay, who thinks that this claim still holds when f has degree 4? Okay, I have a bad news for you. The claim doesn't hold. Let me show you why. Well, I'll show you a counterexample. Let's say, let's take r of x and consider this polynomial x squared plus 1 squared. Oh, this is the polynomial f. So it's presented as a product of two of two irreducible polynomials of degree 2, but it has no roots in real numbers. So it has no roots, but it's reducible. But reducible. So the latter claim holds only for the polynomials of degree 2 and 3. So this is a counterexample in this case. And the reason why the proof doesn't work is because of this thing. When here you have 4, there is a third option where the degree of g is 2 and the degree of h is 2. And then your polynomial is divisible by quadratic polynomial, and doesn't mean that your polynomial has a root. So
Wait, I guess I didn't get the first proof then, because if, let's say, our polynomial has degree 2,
yep.
then can't we just take, I don't know, x plus 1 squared? That's reducible, but it also has no roots.
No. What the claim says,
Oh, wait.
it says that if you have no roots, then you're irreducible. Now,
Oh, wait, sorry,
no.
I was incorrect. Never mind.
Okay, but should I repeat the proof again or clarify it, or it's okay?
Yeah, it's okay.
Okay, no problem, no problem. Okay, so yeah, the claim holds only for polynomials of degree 2 and 3. Now, there is an interesting question. Well, let's take the polynomials over a finite field. Then we have finitely many polynomials of specific degree. For example, we have two constant polynomials. Like let me show it like here. So the polynomials of degree 0 are 0 and 1. The polynomials of degree 1 are x and x plus 1. The polynomials of degree 2, for the degree 0, actually it's 1, and degree minus infinity is 0. That's the correct way of writing. So the polynomials of degree 2 is x squared plus 1, x squared plus x squared plus x plus 1. So we have 4 polynomials. Well, why? Because we have finitely many options for the coefficients. And I want to write down the polynomials of degree 3. Yeah, there are 8 of them, but I will need this list for the next problem. So here we have all these options like plus 1, x cubed plus x cubed plus, just x cubed plus x plus 1, and also x cubed, x cubed, and here plus x squared plus x squared plus 1 plus x squared plus x squared plus x plus 1. Okay, so now I want to find, let's say, all irreducible polynomials of degree 3. So how to find all irreducible of degree 3? Well, there is a way of doing that. We can find all irreducible polynomials of degree 1, 2, 3, and so on. So let me show you. So, well, first of all, how to, well, in this case, in case of degree, well, first of all, let's find all the irreducible polynomials among the polynomials written here. All the polynomials here are irreducible because they're linear. Now, here we have polynomials of degree 2. These polynomials are irreducible if and only if they have no root. Let's check if each polynomial has a root. Since we have z2, there are only 2 options for our root. We need to check 0 and 1. Let's substitute 0 and 1 and check if the polynomial gives you 0 or not. Well, if you substitute 0, this guy and this guy gives you 0, so these are reducible. If you substitute 1, this guy gives you 0 and this guy gives you 1. So this is reducible, and this is the only irreducible polynomial of degree 2. Now, how to check irreducible polynomials of degree 3? Again, because of the previous claim, it's simple. We need to check if a polynomial has a root or not. Well, again, which polynomials have 0 as a root? Well, the polynomials with 0 constant term. So all these guys are obviously reducible because after substitution 0 will get 0. Now, which polynomials give you 0 after substituting 1? Well, the polynomials with even amount of summands. Well, this guy gives you 0 and this one gives you 0. And these 2 polynomials are irreducible because they have no root. This is the list of all irreducible polynomials of degree 3 and smaller. And we can find these irreducible polynomials because of the previous claim. It was simple. Are there any questions regarding what was going on here? Okay, let's try to solve a more complicated task. Let's try to find all irreducible polynomials of degree 4. Here, we cannot use this criterion because polynomials of degree 4, well, it's insufficient to check if they have a root or not. So how do you find all the irreducible polynomials of degree 4? Well, here is the way of doing that. You can list all the polynomials of degree 4. How many of them? There are 16 polynomials. Well, you have to write all of them down. Now, if you, well, I don't want to write all of them down, but let me write some of them. So x to the 4th, x to the 4th plus 1, x to the 4th plus x, x to the 4th plus x plus 1. So these are 4 of them, and let's write some more. And you have 8 more. So here you have 8 more polynomials with the term x cubed. Okay, so now how do you check if a polynomial is reducible or not? Let's say I take this polynomial f. Well, if this polynomial f is reducible, then you can decompose this polynomial into the product of irreducible ones. So it must be a product of irreducible ones. Okay, But what are the options here? So your polynomial f has degree 4. So the sum of degrees of these polynomials must be 4. So what are the options? The option number 1. Well, all of this, you have four linear polynomials. So you have P1, P2, P3, P4, and all of them are linear of degree 1. What is the second option? Well, at least one of them has degree 2. So then you have P1, P2 of degree 1, and P3 of degree 2. What is the next option? Well, you may have P1, P2, this one of degree 1, this one of degree 3. And another option is P1, P2, and both of them of degree 2. So these are all possible decompositions of a polynomial of degree 4 into a product of polynomials, of irreducible polynomials. So, and as you can see, and now you know the list of all irreducible polynomials of degree 1, 2, and 3. So these are these ones. So if you want to find all, so you find all reducible polynomials by finding all these expressions. So you can take 4 linear polynomials, compute the product, you'll get the result, and you just exclude it from the list. And so you go through all the linear ones, and you cover these situations. Then you go through the cases where you have 2 linear and 1 quadratic polynomial, just one case here. And you just exclude from the list all these options. And when you go through all the cases, you exclude all the reducible polynomials. And what remains will be irreducible. Well, this is a straightforward brute force way. Who thinks that he understood the way I'm presenting here?
So if I understand correctly,
Okay.
We need to find all the previous degrees to calculate this one.
Yeah, exactly. So, but now it's very inconvenient to use this straightforward approach. So let me make some optimizations here. You see, when we have these 3 cases, our polynomial is divisible by a linear one. So all these yellow cases means that f has a root. So instead of computing all these cases, you just need to find all polynomials having the root. So the yellow thing just exclude the polynomials having the root. So the polynomials with the root 0 well, when you substitute 0, you will exclude like 8 cases. When you substitute 1, you exclude some other cases. And then, as you can see, the only new case that you need to consider is this one, is the case of product of 2 polynomials of degree 2. But since there is only one polynomial of degree 2 here, this case will exclude only one option here. So it's much quicker than computing all these guys, because you see, you have like 2 options for each element here. So it's 2 to the 4 options. Well, it's less because the order doesn't matter. But if you do it in a straightforward way, then you just have a lot of options. And in order to reduce the amount of options, instead of doing these computation, you just find if a polynomial has a root. So this is the optimization for this specific case. Are there any questions regarding this optimization?
Yeah, I didn't understand it.
Oh, okay, so let me list all the polynomials here again. So I believe I can do this quicker than trying to explain without writing what's written here. And I do this before. I just want to leave all the polynomials without these lines. So x to the 4, 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 x to the 4. Then I need to add x cubed. I just want to list all the polynomials here. And then plus 1 plus x plus x plus 1 plus 1 plus x plus x plus 1. So these are all polynomials of degree 4, 16 of them. Now, I want to, let's say I want to compute these guys. So this will give me a list of polynomials here that I need to exclude. Okay? But now, if our polynomial is represented in this form, it means it's divisible by a linear polynomial. But if you are divisible by a linear polynomial, you have a root. So all these guys have roots. Again, this guy is also divisible by a linear polynomial. It's also has a root. And this guy is divisible by two linear polynomials. So it has a root. So in all these cases, instead of checking these three cases, I can check that our polynomial has a root. Because if it has a root, it's divisible by at least one linear polynomial. So then when you factorize this polynomial into a product of irreducible, you will get one of these three cases. So these three cases is exactly the same as the case f has a root. Was it you?
Okay, yeah, makes sense.
Yeah. So when I want to exclude these cases, I just want to check if these polynomials have roots. So for the case of the zero root, I just exclude the polynomials with the zero free term. These are 8 polynomials having 0 as root. Then if I want to exclude the polynomials having 1 as a root, then I need to exclude polynomials with even number of summands. These are these. And now I have only 1, 2, 3, 4 options. And there is only one. And now I want to exclude these options. I need to take all polynomials of degree 2 and multiply by all other irreducible polynomials of degree 2. But I have only one irreducible polynomial of degree 2. So I just want to compute this product. So what is this? It's x squared plus x plus 1, x cubed plus x squared plus x, x4 plus x cubed plus x squared. And I want to add all of them. And as you can see, you will get x4. Cube will be canceled, x will be canceled. So you have x4 plus x2 plus 1. So this one is also reducible. Let me use a different color. But this one is also reducible because you see, this is from this specific case. And now there are 3 remaining polynomials. And these polynomials cannot be presented as the product of irreducible polynomials of smaller degree. So when this may happen, the only way is when they are irreducible.
Okay, but what did we do in the other case? I mean, in the other method, didn't we also we looked at the previous polynomials that were irreducible, and we
You mean here?
Like here.
But here we check that they do not have roots. It's not enough here. So the yellow lines excluded all the polynomials with the roots. And this one doesn't have a root in Z2, because you see, if you substitute 0 or 1, you will get 1. This polynomial doesn't have a root. But this one is reducible because it appears as a product of 2 polynomials of degree 2. So here we have additional condition. So we have to exclude all the polynomials with a root. And also we need to exclude all polynomials of the form p times q, where, p times q, or p and q are irreducible polynomials of degree 2. I'm not sure that it was clear, but is it okay?
I understand why. I just don't see how that's any different from what we were doing. Like it's
here.
Yeah.
But yeah, it's not different. I mean, I'm just saying that.
But you said it was an optimization.
Yeah, it's just some optimization in order to do it quicker. Because you see, if you Yeah, and here is an important thing. How do I use that every polynomial can be represented into a product of linear ones? Well, in general, if you use just the definition, what does it mean that a polynomial is reducible? You can represent it as a product of two polynomials of smaller degree. So, I mean, in general, you just need to multiply each polynomial of degree 1 by each polynomial of degree 3, or each polynomial of degree 2 by each polynomial of degree 2, and then exclude the polynomials that you have, well, exclude the results. But there are a lot of them. For example, you have like 4 polynomials of degree 2, and you have how many pairs? 4 times 6 pairs, if I'm not mistaken. So you have 6 pairs. So if you use just definition and want to factorize each of them as a product of some polynomials of smaller degree, you just go through all of them. But if you factorize into a product of irreducible ones, you have less options. So as you can see, for example, in this case, you just need to use irreducible polynomials of degree 2 and check that you don't have a root. And a similar procedure works for degree 5, 6, 7, and so on and so on. So, well, you can find all irreducible polynomials over Z2 for a specific degree. If you go through the first degree to the specific degree, step after, well, at each step for computing the new degree. So this is how it works. And the similar way works for Z3 and Z5 and Z7. Well, you just have more options for the polynomials of a specific degree. For example, in case of Z3, you have 3 linear polynomials, 9 quadratic polynomials, 27 cubic polynomials, and 81 polynomial of degree 4, and it's less pleasant, but it's doable. And you can do this using computer, for example. But are there any questions regarding the way how to compute irreducible polynomials over a finite field? Okay. Let's move. Oh, yeah. And now let's do this. Now we know irreducible polynomials. Let's try to factorize a polynomial into a product of irreducible ones. Let's say we have, let's try to factorize. So in Z2 over X. So how do you factorize? Well, first of all, you need to know all the irreducible polynomials. So let's take something like this. And you want to decompose, well, you want to check if it's irreducible or not. And if it's not irreducible, you want to decompose this polynomial into a product of irreducible. Well, when you want to check if it's irreducible or not, first of all, you need to check if it has a root or not. Well, but in general, you need to find all the irreducible polynomials and check if it's in the list of irreducible polynomials or not. Let's see if it's in the list or not. No, it's not in the list. It's not here. It was excluded by this procedure. So now, in general, you need to divide this polynomial by all the irreducible polynomials of smaller degree and check, well, if it's divisible or not. But here, so first of all, you should start from linear polynomials, but checking if it's divisible by a linear polynomial or not is equivalent to checking if it has a root or not. But here you can see that 1 is a root, so it must be divisible by x plus 1. So if you divide it by x plus 1, what will you get? X4 plus x cubed, x plus 1 plus 1, x plus 1, 0. So you can see that this polynomial is represented as x plus 1 times x cubed plus 1. Now, again, x cubed plus 1 is not in the list. It was excluded. And actually, there is a reason why, because it has a root. So now we want, and it has the root 1. So now we want to divide x cubed plus 1 by x plus 1 in order to find its decomposition. So you multiply by x squared, so you get x cubed plus x squared, then x squared plus 1, you multiply by x, and you get x squared plus x. And then you get x plus 1, 1, x plus 1, 0. So now you factorize your polynomial as x plus 1 square, x squared plus x plus 1. And now you see if this polynomial is irreducible or not. Well, it has no roots. And as you can see, it's here in the list. So this is the decomposition of this polynomial into a product of irreducible ones. So you can factorize a polynomial into a product of irreducible if you already know all the irreducible polynomials. So, and this is how you can do this. Are there any questions regarding this computation? Should I clarify something?
I have a question.
Yep.
In this case, we already know that x plus 1, x which is equal to 1 is root. But if we don't know any roots or any irreducible polynomial, what should I do?
Well, you have to find all the irreducible polynomials. That's the only way.
Okay.
So, well, actually, the factorization problem is not an easy task. Well, there are some algorithms doing this factorization, but they're very far beyond of our level of knowledge. There is a Berle-Kemp algorithm for finite fields, which can be applied to use factorization. It actually uses the Chinese remainder theorem for the ring of remainders. But I just don't want to discuss this tool here. We're not ready for that. Okay, so there is one thing that I want to discuss. Let's discuss the Chinese remainder theorem for, well, first of all, the ring of remainders and the Chinese remainder theorem. So I just want to discuss these two things. Okay. Oh, there are two things that I want to discuss actually. Okay, so let me recall the structure of the ring of remainders. I have like 10 minutes. Is it okay if I use like 10 minutes more of the seminar? Okay, so let's say F is a field. And I want to take a polynomial, a non-zero polynomial here. And R is the ring of remainders. Okay, so what is this? So as a set, it consists of all polynomials of degree strictly smaller than the degree of F. Sorry for this, the degree of F. And the plus is the usual addition, and multiplication is actually multiplication modular F. So you multiply polynomials and then take the remainder modular F. Let's take an example. Let's say we consider the ring with real coefficients, and F is x squared plus 1. Okay, so what is the ring of remainders in this case? By definition, is the set of all polynomials of degree strictly smaller than 2. That is the set of all linear polynomials. Okay? So now, let's check how the operation works. Well, the addition is simple. And what about multiplication? Let's try to multiply these two guys. Well, we will, first of all, we need to multiply them as the usual polynomials. So we will get AC plus AD plus BCX plus BDX squared. But then we need to divide this polynomial by x squared plus 1 with remainder. We need to divide by this guy. Well, how do you divide by this guy? Well, we need to subtract with polynomial with coefficient BD. And then we will get the remainder. So the remainder will be AC plus AD plus BCX minus BD. And as you can see, the formula here must be very familiar to you. Do you see what is the formula did we get? Does it remind you something? Okay, so let's recall the definition of the complex numbers. What are the complex numbers? This is the set of all pictures of this form. And if you replace I by X, or X here by I, you will get exactly the rules for the multiplication and addition of complex numbers. So basically, what we have here is the field of complex numbers, where X can be identified with the I. So the ring of remainders for the polynomial ring is the way to produce new interesting rings. And for example, here we can even produce the field of complex numbers. And there is even a way how to, well, there is a way how to establish an isomorphism explicitly. So if I take R of X over X squared plus 1 and C, I can map A plus BX to A plus BI, and one can check that this map is a bijective homomorphism. Well, first of all, it's clear that it's bijection, because the set here consists of pictures like this, and the set here consists of pictures like this. So it's a bijection. We just replace the symbol X by symbol I, and nothing changed. But then these formulas show that if I add the elements of this ring here and then replace X by I, this will be the same as I replace X by I and then add the numbers as the complex numbers. So these formulas show that the addition here is exactly the same as the addition here. And the second formula shows that the multiplication here is the same as multiplication here. So this map preserves both operations. So this is an isomorphism. Okay, who thinks that the example is clear? Okay, Kirill is here. But are there any questions regarding the example? Okay. So, but let's try to, oh, sorry. Let's try to discuss a different example. Well, let's do this. Let's take Q of X and let's take a quotient by polynomial. Well, let's say x cubed minus 2x. Well, let's check what we will get. How to understand the structure of this polynomial ring, of this ring. Well, by definition, it must consist of polynomials of degree 2, where A, B, C are rational, and the addition is usual, and multiplication is taken with respect to this polynomial. So we multiply polynomials here and take the remainder. So, well, it's very hard to understand the structure just looking at this representation of the elements. Instead, we can use the Chinese remainder theorem for this ring. Indeed, the polynomial x cubed minus 2x is actually a product of two polynomials, x cubed and x squared minus 2. And these two polynomials are co-prime. Their GCD is 1. So by the Chinese remainder theorem, we know that there is an isomorphism like this. And how does it work? Well, it takes a polynomial here, and it takes this polynomial f modular x, and here f modular x squared minus 2. And this map is an isomorphism of rings. So now let us see what happens here. Let's try to describe, oh, yep, that's very inconvenient. So let's try to discuss, or let's try to describe the first factor. What is this factor? Well, now I want to address two questions. The question number one is how to describe this and this factor, and the question number two is how to find the inverse map. Well, the question how to find the inverse map is very similar to the question how to find the inverse map in case of integers. So there is a similar procedure, but let's discuss this guy. So what is Q of x modular x? Well, this is the set of polynomials of degree strictly smaller than the degree of x. So these are polynomials of degree 0. So these are constants.
Just a Q?
Yeah. So, but as a set, it's a Q. But let's check that the operations are correct. So the addition is definitely the same as the addition of Q. But what about multiplication? But in case of multiplication, if you take two rational numbers and if you multiply them, they will be a polynomial of degree 0, which is smaller than x. Well, I mean, the degree of a times b is 0, which is smaller than 1. So you don't need to take the remainder with respect to x. So the multiplication is also the same as the multiplication in the in Q. So this is just the Q as a field. No, well, as a ring. I mean, plus and multiplication are the same operations as the operations on the rational numbers.
Okay.
So is it clear now?
Yeah.
Yep or not?
Yeah, it's clear.
Oh, okay. So yeah, and let's discuss this map. When you take f modular x, it's actually, what does it mean? When you take a polynomial like this, modular x, the result is just a, which is f of 0. Well, when you divide by a linear polynomial, you're just computing the polynomial at the root of the linear polynomial. So actually, the first factor here is just q, and this thing is just f of 0. Well, the second factor is less convenient to understand, but But in order to understand the second factor, I need to explain one additional result. But instead of doing that, I want to address a different question, is how to find the inverse map. But before switching to the second question, are there any questions regarding what I was explaining here?
Yeah, I have a question. Why isn't f of 0?
Oh, again, if you have a polynomial f, what is the remainder of this polynomial with respect to x? You just want to cancel all the powers of x, and the free term will be the result.
Okay.
And in general, oh, I'm sorry. In general, if you have a polynomial f and you want to take its remainder modular a linear polynomial, it's f of alpha. If you have a linear polynomial x minus alpha, then a remainder of f with respect to x minus alpha is actually f of alpha. Well, because if you have this, so R must be a polynomial of degree strictly smaller than the degree of x minus alpha, which is 1. That means that the degree of R is either 0 or minus infinity. So R is either, R is constant. And if you substitute alpha instead of x, you will see that f of alpha equals q of alpha times 0 plus R. So R is equal to f of alpha. So if you want to find a remainder with respect to a linear polynomial, it's just finding the value of your polynomial at this root. Okay, are there any questions regarding this? Okay, so now how do we find the inverse map in this case?
We
Well,
need to use this equality where 1 is equal to.
Yeah, we need. So we need to. Let me recall how it works. Well, I'm sorry for this. It's just really inconvenient. Just give me a second. I just copy paste what's written here in order to save some time. And I'll do it like this. Okay, so let's go here. So first of all, we need to find two polynomials, S1, which goes to 0, 1, and the polynomial S2, which goes to, oh, the first one is 1, 0, the second one is 0, 1. And if we can find these guys, then a pair, let's say FG, must go to S1 times F plus S2 times G modular, well, and here modular x cubed minus 2x, x cubed minus 2x. So this is how the inverse map works. So if we can find two polynomials going to these specific ones, then we can check that this polynomial goes to this pair, because when you take this one modular x, S1 goes to 1 and S2 goes to 0. So this thing modular x will give you f. And if you take this thing modular x squared minus 2, then S1 gives you 0 and S2 gives you 1. So this dies and this thing gives you g. So this polynomial, its degree could be larger than 2. So in this case, we should take the remainder modular this thing. But if not, then this polynomial is an element of this ring, and its image is exactly this pair. So we have found a polynomial corresponding to this pair. So this is how to find an inverse of this pair using these two special polynomials. Are there any questions regarding this? But that.
No.
This is exactly the same as we did for integers. And now how to find these polynomials S1 and S2? Well, we know that, well, in our case, x and x squared minus 2, they are coprime. So we can represent using extended Euclidean algorithm this greatest common divisor as a linear combination of this form. Then, if you consider 1 minus u times x, this will be exactly the same thing as this product. And as you can see, this thing gives you 1 modular x and gives you 0 modular x squared minus 2. So this is your S1. And for S2, you do the same, but with the second summon. And this is your S2. So you may take this, oh, I'm sorry, this as S1 and this as S2. This is how to find them. So exactly the same thing as we did with, okay, with integers. Are there any questions regarding this part? So again, the most annoying part here is just to compute this representation of the GCD as the linear combination of the initial polynomials with some polynomial coefficients. But oh well, if you can do that, you can find these polynomials and you can find the inverse map for this one.
I think I didn't get it. How to find U and V?
Okay. Oh, how to find U and V? This is, okay, this is a GCD. So this is the problem we discussed at the beginning of the seminar. So you divide one by another one. Well, okay, let me do it like this. Let's move to the beginning of the seminar. You see, here we discussed how to find a GCD and how to find these elements U and V. This was the algorithm. So you divide, so these are your polynomials, so you do this computation. This will be a GCD, and when you substitute all these expressions, you will get the expression for GCD as the linear combination of the initial polynomials.
Okay, so and we know that GCD is 1. This is why we have 1 on the left side.
Yeah. The GCD is 1, so that's why we can do this.
Okay. Okay.
But yeah, in general, when you use this algorithm, you will get your GCD will be not necessarily 1. It could be something like 5 or 7. It's not non-zero coefficient. So you will represent, let's say you compute this and R2 will be something like 5. Then you express 5 as a linear combination of f and g, and then you divide everything by 5, and then you get the expression of the element 1 as a linear combination of the initial polynomial.
Okay, gotcha. Thank you.
Okay, so that's basically it. Yeah, I thought I would be able to explain one additional result, but I believe I can leave it for the next time. It's not a big deal. Are there any questions regarding the seminar, or probably some other questions?
I have a question about the lecture. Probably I skipped it, but we have a, how do we call this set? Do we call it a set of all reminders?
Yeah, this is the ring of remainders.
Reminders, okay. And do we have some properties for it?
Well, what kind of properties do you expect? I mean, you know exactly how the set of elements look like here. You know exactly the rules for the operations, and you know the Chinese remainder theorem. This is basically everything we know now.
And it's not a ring, no, not something else.
Well, no, it's a ring. It's a ring of remainders. It's a ring.
Why it's a ring?
Okay, I didn't prove that this is a ring, but we can check that this is a ring. But okay, so if you want me to do some computations, so let me move here. So in order to check that, well, so we want to check that this is a ring. Yep. So we have all polynomials of degree strictly smaller than f.
Yeah, we have all operations, so we can just check the properties.
Yeah, we need to check the properties. And the most interesting one So the properties for the addition are obvious because the addition here is the same as the addition of polynomials. So we need to check the properties for multiplication. First of all, associativity. So how do you check this? So you take 3 different polynomials from here. Now you need to compute the product, this product.
This is clear.
Yeah, so yeah, but I want to finish. So how do you, well, how do you compute all of this? So you multiply these two guys and you find the remainder modular f. This is R1. And then you multiply R1 with G3 and find its remainder modular f. And the left-hand side, by definition, will be R2. And then you repeat the same thing for the right-hand side, and then you need to prove that the remainders you have are the same. But using these equalities, you can prove that the remainders are the same. Should I do this, or is it clear?
No, it's clear.
Okay. So this is why I skipped all these computations. It's not that interesting. But if you have, well, I would suggest try to do all this computation. At least check that multiplication is associative. It's a good exercise. And you will understand the way this ring works if you do this computation. But and if you have some problems with this computation, you might ask me, and I will write you down how to, and I'll write down how to do this.
Okay.
Other questions?
Yeah, could you show the beginning of the seminar, please, again? Like the same task with the GCD and finding coefficients.
No problem. Yep.
I kind of forgot it. How should I find those coefficients? Just substituting all reminders in the back order?
Yeah, you see, this guy is a GCD. Now, you can express this guy as a linear combination of G and R1. You see, you can move this to the left, and this is 1 times G minus, and then R1 came from here, and you can substitute instead of R1 a linear combination of F and G. So going from up to, well, actually, I would rather suggest go from up to down. So first of all, you substitute the representation of R1 as a linear combination here, and then you substitute everything here, and so on and so on.
Okay, could you show an example?
Okay, so the example is here. So, well, we have R2, it's G minus X plus 1 R1. So this we have from this equality.
Okay.
For R1, we have F minus G. This is from this equality. So we have these two expressions, and R2 is our GCD. So now I just substitute R1 here, and I substitute G minus F instead of R1 because R1 equals F minus G, and I will do this expression. And this is the answer.
Okay. Okay, thank you.
No problem. Are there any other questions? Any type of questions?
I have a question about our future exam.
Okay.
Is it supposed to be online or offline, probably?
Yeah, it will be online.
And are we going to have an oral test?
What again?
Like colloquium or oral test?
Oh, no, we don't have oral test. The exam will be oral. The test will be written and the exam will be oral.
Okay, and do we have to know theory or proof of some theorems?
Okay, so the purpose of the written test is to check how you can solve the problems. So for the test, you need to know how to solve the problems. And the problems will be similar to the ones you solved during your homework or during the seminar. So you will never encounter anything beyond the scope of the seminars on the test. So if you, the reason for the seminars is to prepare you for the test. So I want you to know how to solve all the problems. So if I tell you to compute something, you can do this, and you understand all the terms. That's the reason for the test. The reason for the exam is to check that you understand the theory. So during the oral exam, I'll ask you to do three things. The thing number one, to formulate several definitions. So I want to check that you know all the terms, all the definitions. The second thing, you need to formulate claims, important claims. So I do not ask for technical claims, but the important claims like the Chinese remainder theorem for integers, or Chinese remainder theorem for the ring of remainders, and something like that. So you need to know these things. And the third part will be to give a proof for a claim. So there will be three parts, and these are all of them. So yeah, that's it.
Okay, thank you. And back to the claims, I missed it. We know that from today's seminar, we know that if our polynomial has degree either 2 or 1 or 2 or 3,
okay,
and it has a root,
okay,
the root, we know that it's reducible.
yeah, it's reducible.
Yeah, and what about degree 4?
Well, in case of degree 4, it's not true that it has no roots, then it's irreducible. It may have no roots, but it's still reducible. And this is a counterexample.
But the question is it always false, or just it's not correct?
Oh, you mean is it true that for every field you can find a polynomial of degree 4 such that it has no roots, but it's still reducible?
Yeah.
Well, if your field, well, for example, for complex numbers, it's not true, because in case of complex numbers,
always have roots.
Yeah, if you have, well, if you're reducible if and only if you have a root, because, well, the only irreducible polynomials are linear ones. But if you take rational numbers or real numbers, then this is true, because you have irreducible polynomials of degree 2, and if you multiply two irreducible polynomials of degree 2, you will get a polynomial of degree 4, which has no roots, but it's reducible.
Okay, but in general, apart from the field, we have application only from the right to the left.
What do you mean by so if it's
if we have a root, it means that our polynomial is reducible.
Yeah.
Okay. Okay, thank you.
No problem.
A lot.
So am I right that the list of questions is depleted?
Yeah.
Okay, no problem. Well, guys, thanks a lot.
Yeah, the last question.
Okay.
When are we going to post the homework?
Okay, I hope this evening, because tomorrow and Saturday I won't have time for that.
Okay.
But this evening, really late.
No problem. Just in case, because we're going to do it tomorrow.
Okay.
Okay, thank you very much.
No problem. Thank you.
Have a nice
Bye.
weekend.